What time is it? It's science time.
Science time. Let's all stop and just unwind. 1, 2, 3, 4, here we go. Learn so much your brain explodes. Lessons so cool, so fresh. Beat so big you'll lose your breath. Learning facts and real cool stuff. Scream for more, can't get enough. It's science time. It's fun, you best believe. Explore and learn new things. Come and join me, please.
I'm Mr. C, and this super smart group is my science crew. Lila is our notebook navigator, Alfred is our experiment expert, Riley is our dynamite demonstrator, and London is our research wrangler. Working with my team is the best and makes learning so much fun. Actually, you should join us. Today, we're learning about static electricity. What time is it? It's science time. Welcome back to another episode of DIY Science Time. I'm Mr. C, and I'm so glad you're here to be part of our crew today. We are talking about static electricity. It's going to be shocking. It's going to be electrifying. It's going to be amazing. And I have a top secret science secret for you. I use static electricity each day to do my hair. Yeah, how else could I make this hair stand up like that without a little bit of help from static electricity? And with your help, we'll have some amazing experiments we can conduct together today. Alfred, what are they gonna need to get started?
You might be shocked with how much fun we're going to have today. You'll need the following materials: balloons, a plastic bag, a towel, scissors, a styrofoam cup, and of course, our science notebook.
A science notebook is a tool that every scientist should have, and it gives us a place to record all of our learning. Taking good notes and being organized allows us to be better scientists. A science notebook allows us to go back and review all the data and information we've gathered during our experiments. Plus, it allows us to share results with other scientists who might be interested in learning more about what we've discovered. Whenever you see the notebook pop up on the screen, like this, it's a reminder that this is a good place for us to jot down new information. You can see I've already added a title and a list of materials for today's activity. Our crew is still going to have lots of information to collect and organize as we go through the experiment, so keep your notebook handy. Most importantly, the more you use the science notebook, the better you'll get at taking notes and recording data. If you don't have a science notebook yet, download a copy of Mr. C's science notebook from the website.
All right, let's get started. I've got a balloon and I've got some materials we're going to test. I've got this little bit of confetti stuff I'm gonna plop down here on the paper so we can see it. And then I also have some pepper that we're gonna bring over here. And I have this aluminum can we'll get to as well. We're gonna take this balloon and we're going to blow the balloon up. Tie it off. And I'm just going to bring it over my paper. Nothing happens. I'm going to bring it over my pepper. Nothing happens. I'm going to bring it right here over my can. Nothing happens. So the question is, what if I take this balloon and rub it on my towel? Is it going to change anything? Can you hear it? The paper's reacting to our balloon now. That is peculiar. Let's see if it does anything with the pepper. Did you see that? Did you hear that? Can you still hear it? That is amazing. The pepper literally... It's about to make me sneeze, so I apologize for that. The pepper literally jumped off of the paper onto the balloon. And it's all over the balloon now. I want to do the soda can, but I think we need to clean that up here just a little bit. So let me clean that up really quick. Now we've got all that pepper picked up. We don't have any more pepper problems, but we still have this aluminum can to test, and I want to give this a try. So I'm going to set this here. I'm going to put this balloon over here. It's not responding. Maybe a little bit. No, that's just me blowing the air like that. But I'm going to take this balloon now, and I'm going to rub it against my towel. Now, wow, whoa, look at it responding to this balloon. That was awesome. The question is, what is actually going on? We need to figure this out so we can better understand what's happening to the balloon and to the can. Static electricity is a stationary electric charge and is typically produced when two objects rub against one another. This creates an imbalance of electric charges within or on the surface of a material. The static charge remains there until it's able to move away by electric current or electrical discharge. Static electricity is electricity that doesn't move and flow like normal electricity, but it can create sparks, crackling sounds, and even attract dust or hair. Understanding the basics of static charge will allow us to hopefully make a plastic ring levitate above a balloon. So let's get started. You're going to need your balloon, a plastic bag, some scissors, and your towel. Now I have two types of plastic bags. I have this little plastic bag, and then I also have this bigger bag that I got at a grocery. I'm going to start with this green bag because it is smaller, and I'm hoping that the smaller bag works better because there's less mass to it, and yeah, we just hope it works. First thing you're going to do is you're going to unfold your bag, try to get it as smooth as possible. And I'm going to cut off the bottom. Try to get a straight cut out of it. And then I'm going to cut just a small little sliver off of the bottom now. All right. Now what I'm going to do is I'm going to open it up. Ah, staticky already. And there I have my plastic ring. Okay. Now, what we're going to do next is we're going to take a balloon. I'm going with a blue balloon. I'm going to make it so I can hold the balloon with my hand. There we go. I'm going to be able to rub the balloon with one hand, and then I'll be able to hold my other ring with the other so I can kind of work together. If you have a partner or a family member, this is where they're super helpful, because you'll need an extra set of hands potentially. All right, I'm going to take the balloon, rub it against the towel. You can actually hear the static. And the towel's reacting, look. The towel's actually reacting to the balloon. And now I'm going to take this. Ah! It's so dry in the house right now. I'm going to do this. I'm going to let go. Wait a minute, it sticks? I thought it was supposed to float. Look at that though. It's like half sticking, half floating. If it's sticking to it, wait a minute. Like charges repel and opposite charges attract, so I did not expect this to happen at all. But I wonder if I take this off, if I charge this again, I probably have to charge both. Look, it's, oh, that was cool. All right, so what we're gonna do, it's actually attracting, look, it's attracting, it's standing straight up. I did not expect it to be like, oh, that's so cool. So if the green bag is coming to the balloon, that means they have opposite charges, they're attracted to one another. So in order to make this levitate away from the balloon, we're going to need to have them have the same charge. So we need to rub them both against this towel. I'm just amazed that it's doing this. I didn't expect it to do this. All right, so I'm gonna set this over here for a second. I'm gonna rub that all over this. I'm gonna get that charged. Now I'm gonna take this, rub it all over this. Now for lucky, they should have the same charge. Like charges should repel. Did you see it? Let's try that again. Oh, that's so cool. I'm gonna slide back. We're gonna try it again. Static electricity at work here at my house. I should have made the balloon a little smaller. It's really hard to hold with one hand. All right, I'm gonna rub this in here. Ah! There we go. Oh, that is so awesome. That is so cool. All right, we gotta try that one more time. Rub this over this. That is so much fun. That is so much fun. All right. So we're gonna get this charged. And then we're going to charge this as well. And now we're gonna try to drop this. It's stuck to my hand. There we go. Static charge. Have some fun. If you have a smaller bag, give it a try with a smaller bag, or you could try it with a larger bag to see if it has the same effect on the plastic bag with the larger one. So much fun. You've got to give this a try. Have some fun with your family. Do some races across the house or across the living room. Yeah, static electricity.
We're really charging up our notebook with cool information. I included a few drawings of the levitation ring and also added a note that like charges repel one another and opposite charges are attracted to one another. I wonder what would happen if you try the experiment with a bigger plastic ring or a different size balloon. Would that impact how the ring levitates? I think that's definitely something that should be tested.
You can also use the power of static electricity to bend water. That's right, charge up that balloon and bring it towards the running water. The negative charges in the balloon are attracted to the positive charges in the water. This causes the stream of water to bend.
Oh my gosh, I've made the biggest mess I've ever made with salt and pepper. All these experiments, and I have the salt and pepper here. I just don't want to waste it, but it's all mixed up. There's no way I'm going to be able to get this separated easily. Yeah. This is going to take forever. Wait a minute. I just had a great idea. What if I use static electricity to try to separate these two? The balloon worked earlier to lift up the pepper, but I wonder if one of these plastic spoons would also be able to work. There's only one way to find out. Oh my goodness, look at all the pepper that I got off of there. One spoon. Charge this up. 2 spoons worth. The pepper is light enough and it's attracted to that spoon because they have opposite charges that it jumps out away from that salt. The salt is heavier, has a greater mass, and doesn't come off the paper. It's gonna take me a couple of minutes, but I'll be able to salvage all of this pepper and all of this salt so I can go make a spectacular science dinner. Yes! Static electricity just sparks me, and the energy is just amazing. All right, I gotta finish this.
Want to take your static powers to the next level? Make a quick batch of bubble solution and blow a bubble on the table. charge your wand and make that bubble move. Before you know it, you'll have bubbles slide to the right and slide to the left.
Oh, that's so cool.
An electroscope is a scientific instrument used to detect the electric charge on an object. To test the electroscope, charge an item, move it close to the copper wire edge, and then watch the aluminum spread apart. The electrons from the object transfer to the copper wire and move through the wire. When the electrons are pushed down through the wire, they are transferred into the hook and into the aluminum foil. Because both pieces of foil have a negative charge now, they want to repel. Hop online to download the activity sheet to build your own electroscope.
Thanks, Alfred. Electroscopes are really cool. And that copper wire that was in the cup, well, that copper wire is also in my simple circuit that I built right here. As you can see, I have wires connected to a light bulb, and it comes back to a battery. However, the light bulb's not on right now. When I connect these wires, the light bulb turns on. That's because electrons and current are able to flow easily through the circuit. When I disconnect it, the electrons quit flowing. We can also use this idea to help us better understand insulators and conductors. An insulator doesn't allow electrons to move through it. Conductors allow electrons to move easily through them. That's why some objects will turn on the light bulb while others won't. I've got a couple we should test. Let's do this. First thing, I have an aluminum strip. When I put the aluminum strip into our circuit, it lights up the light bulb. This is a conductor. Set that over here. We have a plastic spoon. When I put the plastic spoon into the circuit, the light bulb does not light up. This tells us that the spoon is an insulator. I've got a metal spoon. When I put the metal spoon into the circuit, the light bulb lights up again. Tells me that this spoon here is a conductor. All right, I've got a couple more. I've got an iron nail. And when I put the iron nail into the circuit, the light bulb also lights up. So that means it is a conductor. Then I have a copper wire here that has some insulation on the outside. Oh, did you hear what I just said? All right, so I've got the wire here. I'm gonna put the wire on there. I'm gonna connect that, and it lights up the bulb. But if I take and put the alligator clip on the insulator on the outside part of the wire, the rubber part, it doesn't light up the light bulb. So this wire has an insulator with a conductor inside of it. So it has both. We'll put this right here for now. And lastly, we have our balloon. So when I put the balloon into the circuit, it's a latex balloon, and it does not light up our light bulb. So we can say that this also is an insulator. What does this all mean? Well, I have two insulators, I've got these three conductors, and I've got this combo here. But what's interesting is static electricity is just that. It's a static charge. And so objects that don't allow electricity to move through them easily, like a spoon and a balloon, hold a static charge. Because when the electrons get onto that surface, they don't really go anywhere. And the only way they go somewhere is if they discharge onto another object. Hence, static charge, hence being shocked. So that is how we use conductors and insulators to better understand static electricity. These here won't hold a static charge because electrons move through them easily. These two objects over here do. Test some things at your house to see which objects are better insulators and to see which ones hold a better static charge. Give it a try.
Have you ever reached for a metal doorknob and felt a zap? If so, you've experienced static electricity in your home. By dragging your feet across your carpet,
you transfer more electrons to your body. Those electrons are attracted to opposite charged items like your metal doorknob. As soon as you get close enough for the electrons to jump, you get a mini bolt of lightning. Yikes! Ouch! That's a shocking event.
You may be shocked to find out that some materials hold electrons better than others. And you may also find it very interesting to know that some materials give up electrons more easily than others. In fact, scientists have ranked materials in order of their ability to hold or give up electrons. This ranking system is called the Triboelectric Series. If we choose two objects and rub them together from the list, we'll create a static charge. Under the right conditions, the material higher on the list will give up electrons and become positively charged. That also means that the object lower on the list is collecting electrons and becomes negatively charged. We've actually used this a number of times today during our experiments. When we rub the balloon against our hair, we lose electrons to the balloon. The balloon now is negatively charged and we are positively charged. As we bring those two things together again, the hair is attracted to the balloon because opposite charges are attracted to one another. We also used fur in a PVC pipe to make the bubble on the table move. When the fur was rubbed against the PVC pipe, it gave up electrons to the PVC pipe, causing the pipe to become negatively charged. The PVC was so negatively charged that the soap bubble was attracted to it and glided across the table to try to get to it. Try conducting some experiments of your own to test some of these objects on the list.
Lightning is a buildup of electrical charges in a cloud, and those charges are attracted to objects on the ground, like a house. Fortunately, Benjamin Franklin invented the lightning rod in 1752 to help protect buildings. Lightning rods safely attract and move electrical energy from a lightning bolt to the ground and reduce the risk of a lightning strike.
A Van de Graaff allows us to see static electricity in the lab, and it also allows us to do some really cool demonstrations. And the first thing is, we're going to try to put some confetti onto the dome. Let's see what happens when we turn it on. Whoa! The confetti has the same charge as the dome and shoots off of the dome because they are repelling one another. A Van de Graaff is able to generate electric charge very rapidly and behaves similarly to when we are rubbing the balloon against our head. The rubber belt inside carries away the negative charges, while the roller at the top inside the dome accumulates a positive charge and places it on the dome. This scientific tool was invented by Robert J. Van de Graaff. Whoa! I didn't expect that to happen. Oh, what if we try taping down some toilet paper? Oh, let's turn it on and see what happens. Yes! It looks just like hair standing up on a person who might be touching the Van de Graaff. It's really amazing to see the spark that's generated by the grounding rod as we put it close to the charged dome. That huge spark is similar to the little spark you feel sometimes when you touch a doorknob. But this one happens to be a lot bigger and a lot stronger.
All of this information has sparked my curiosity. I didn't think getting zapped by my doorknob was really a mini bolt of lightning. That's so cool! I've also organized the insulators and conductors into a chart and noticed that the insulators are better at holding static charges. The balloon is made of rubber, the spoon and bag are made of plastic. And because they are insulators, it makes sense that they don't allow electricity to flow easily, which makes them perfect for holding a static charge.
Have you ever opened up your clothes dryer to find socks, sweatshirts, and pants all stuck together? If so, you've witnessed static electricity. Because those items have been tumbling and rubbing against one another in the dryer, they often have different charges and find themselves attracted to one another. Dryer sheets were invented in 1969 by Conrad Geiser to reduce the buildup of static cling.
That is so much fun. Look, it's stuck to my hand. Ah! Static charge. Always fun, always electrifying. And you know what? My science crew did an amazing job today. And I'm not even shocked about that because when we learn together, we have so much fun. And speaking of fun, if you haven't done it yet, you should download a science notebook from the website so that you, all right, I'll hold on to you, so that you are able to take notes and supercharge your learning with your science notebook. It's a great place to keep track of everything you're doing so that you remember things that you discovered and learned, and you can go back to it and review it with your friends and family. Whether it was our levitating ring, our rolling can, or even this electroscope. Isn't that just the best? Keep learning, keep exploring, keep having fun, and remember, science is wherever you are. See ya. Bye.
It's science time.
Top secret science secret.
It's science time.
Wow. Yes. No more pebble problems. While a conductor does allow electricity to move, an insulator does not allow. Oh.